welcome back to Cryptography and Network Security series. In this video, we'll be speaking about polyalphabetic ciphers. We'll understand how Vigenère cipher works. We'll look into Vernam cipher, and we'll also speak about one-time pad and how it actually functions. So let's get started. So the first topic which we come across is polyalphabetic cipher. Polyalphabetic cipher is one amongst the substitution cipher techniques, which will make use of multiple alphabets or shifting patterns to encrypt a given message. When we were speaking about the monoalphabetic cipher in previous videos, so here we were using a single substitution rule throughout the message. But speaking of polyalphabetic ciphers, we will apply a series of different substitution rules. So by making use of this technique, it becomes more challenging for the attacker to understand or use the frequency analysis to crack the code, because here each letter may be encrypted in multiple ways. So depending on the chosen rule for that part of the message. So this cipher applies multiple related substitutions, and we make use of a key to determine which rule has been applied to each character in the given message. So this is what it comprises of. Now let's look into the Vigenère cipher. So it is one of the most well-known polyalphabetic ciphers, and it uses a sequence of Caesar cipher. It uses a sequence of Caesar ciphers with different shift values determined by a keyword. So here, for example, each letter of the keyword corresponds to a shift in a Caesar cipher. So first we prepare a keyword that is repeated till the plain text length, and then we find equivalent numeric value and apply the formula. So this is the formula which we have: Ci, that is ciphertext, is equal to plain text plus key, and we take the modulo of 26 here. So let's look into an example here. So the plain text is we are discovered save, and the keyword is deceptive, DECEPTIVE. Okay, so first let me write down all the plain texts here. We are DISCOVERED SAVE. So I have written down all the plain text here. Done. Next I have the key. So along with the plain text, I have also written down the numeric values. So for W it is 22, for E it is 4, for A it is 0, for R it is 17, and so on. Now let me write all the keys. So here we had seen in the rule that we have to repeat the key till the plain text length. So here deceptive is very tiny compared to this big sentence, right? So you have to repeat it till the end. DECEPTIVE. Done. Again DECEPTIVE, again D. So here we have covered all the keys. Next, writing the numeric equivalents of D of the keys. So for D it is 3, for E it is 4, for C it is 2, for E again 4, for P it is 15, and so on. That's how I have written down. First for the plain text I wrote, and for the key value also I have written the numeric equivalents. Now I will add up the plain text value along with the key value. Let me add these and write it here: Pi plus Ki. So if you add 22 plus 3 is 25, 4 plus 4 is 8, 0 plus 2 is 2, 17 plus 4 is 21, 4 plus 15 is 19, 3 plus 19 is 22, 8 16, 18 plus 21 is 39. Let me write it down here. Then we have 2 plus 4 is 6, 14 plus 3 is 17, 21 plus 4 is 25, 4 plus 2 is 6, 17 plus 4 is 21, and so on. So we have written P plus Ki value here. That we are done with finding the P plus Ki value, next step is to perform the modulus of 26. So in order to find P plus Ki mod 26, we'll be getting the cipher text. So here, if P plus K value is less than 26, then this P plus K is the same value, is the result. If P plus K is greater than 26, then we have to subtract P plus K minus 26. We'll look into this as to how it is actually solved. Okay. So here I have 25. So 25 mod 26. So 25 is less than 26. So I'll write 25 as it is. Again 8. 8 mod 26 is 8 itself. Next I have 2 mod 26 is 2 again. So let me write down for 25 equivalent is Z. So I have written Z here. For 8 equivalent is I. So I have written I. Then 2 equivalent is C. Next I have 21 equivalent is V. I have written V. Next I have 19 19 equivalent is T. So I have written T. Next I have 22. 22 equivalent is W. Next I have 16. 16 equivalent is Q. Then I have 39. 39 mod 26. So I have 39 here. So 39 mod 26 means P plus Ki minus P plus Ki minus just 13. I get the result as 13 here. So 13 is again N here. So I have to write N here. Next I have 6. 6 is G. N here again G. And then 17. 17 is R. So I have written R here. Then 25. 25 is Z. Then 6. 6 is G. 21 is V. 19 is T. 22 is W. 0 is A. And 21 is V. And then 25 is W. And again W. So here this is how I get the complete cipher text. So this was about the Vigenère cipher. So speaking about the strengths and weaknesses, strength of Vigenère cipher is that there are multiple ciphertext letters for each plain text letter, one for each unique letter of the keyword. So by having this, it makes difficult for the attacker to understand the letter frequencies and patterns. However, it is still susceptible to certain cryptanalytic techniques, such as determining the keyword length by analyzing repeating patterns in the ciphertext. So once the key length is known, the ciphertext can be easily broken by treating each segment as a separate Caesar cipher and analyzing the frequency distributions with each segment. So in conclusion, we can say that the Vigenère cipher's periodic key-based encryption provides a stronger security compared to the single substitution methods, but can be cracked with sufficient ciphertext and statistical analysis. So all improvements achieved over PlayFi cipher, but considerable frequency information remains. So let's look into this example. We'll solve this example now. So I have a keyword as BANGALORE and plain text is this. So let me write down the plain text first. INFORMATIONSCIENCE, and I have to write Bangalore now. BANGALORE, BANGALORE. So I am done. Now I have to directly write the now let me calculate the numeric equivalents of this Pi plus numeric equivalents of Ki and write it down here. So I and B, for I it is 8 and for B it is 1. 8 plus 1 is 9. Yeah, I'll write down 9 here. Next, N and A. For N it is 13 and A it is 0. So 13. F and N. For F it is 5. For N it is 13. So 18. I've written 18. Next, O and G. O is 14 and G is 6. So 20. R and A. R is 17, A is 0. So 17. M and L. M and L I have 12 plus 11, that is 23. Then A and O. O is 14. And then T and R. For T and R it is, I have 36. And for I and E, 12 I have. Then for O and B I have 15. Then 13, 31, 8, 8, 27, 19 and 8. So here I have P plus Ki value. Now let me do the modulus of 26 for this and write down the values here. So 9 modulus 26, 9, 13 modulus 26, 13, 18 modulus 26, 18, 20 modulus 36, 20, 17 modulus 26, 17, 23 modulus 26, 14 modulus 26, 14, 13 modulus 26, that is 36 minus 26, that I get as 10, 12 modulus 26, 12, 15, 13, 31 minus 26, 31 minus 26 I get 5. Next 8, 8, 27 minus 26, 27 minus 26 is 1, right? So 1 I can write here. Next 19 and then 8. So let me write down the equivalents for all of this. 9 equivalent is J, 13 equivalent is N, 18 equivalent is, what is 18 equivalent? R, 18 equivalent is S, sorry, 20 equivalent is U, 17 equivalent is R, then 23 equivalent is X, 14 equivalent is O, 10 equivalent is K, 12 equivalent is M, 15 equivalent is P, 13 equivalent is N, and 5 equivalent is F, and then we have 8 so we have I followed by 1, that is B, and then 19 we have T, and again I. So this is the ciphertext which I obtained. So this was about the Vigenère cipher. Now let's look into Vernam cipher. Vernam cipher is a polyalphabetic cipher known for being theoretically unbreakable when used with a key that is as long as plain text, entirely random and used only once. So this cipher was invented by AT&T engineer Gilbert Vernam in 1918, and it operates on binary data, that is in bits rather than on letters. So this design leverages the properties of XOR, exclusive OR operation, which allows both encryption and decryption through simple bitwise manipulation. Simple bitwise operation is being performed here. So if you see, we take help of the key stream generator. Along with that, a cryptographic bit stream ki is given and plain text is taken. So pi mod pi XOR ki operation is done in order to get the ciphertext. Once ciphertext is obtained, again by taking use of the key stream generator algorithm or function, again we take ki plus ci, performing XOR operation on it, we get the plain text back. So his system works on binary data rather than letters. The system can be expressed successively as following. This is the equation where pi is for ith binary digit of plain text, ki is the ith binary digit of key, ci is the ith binary digit of ciphertext, and here we have is the XOR operation. So ciphertext is generated by performing the bitwise XOR operation on plain text and key. Because of the properties of XOR, decryption simply involves same bitwise operation. So as we discussed here, bitwise operation is same for encryption and decryption. So next, let us consider this example where the plain text bit sequence is P is equal to 1101 and key value is 1011. So we have to perform encryption. So 1 XOR 1 is 0 and 1 XOR 0 is 1, 0 XOR 1 is 1 and 1 XOR 1 is 0. We know how XOR operation is done. So we get the ciphertext 0110. Now decryption is reverse of here we have 0110 and here whatever the key was there same. So 0 plus 0 XOR 1, 1, 1 XOR 1, 0, 1 XOR 0 is 1, 0 XOR 1 is 1. So here I have obtained back the plain text. Plain text here and here both are same. So this was about plain text. Speaking of the key requirements for security, so the strength of Vernam cipher is referred to one-time pad where the key is random and it can be used only once. It relies on specific conditions. So here the key must be as long as the plain text, the key should be truly random and there has to be no statistical relationship with the plain text. Along with that, the key must not be reused again. When all these conditions are met, no, the ciphertext can be theoretically secret, making it unbreakable throughout the cryptanalysis. So this was about the Vernam cipher. Let's now look into one-time pad as we discussed about one-time pad. So one-time pad is the improvement of Vernam cipher that yields ultimate security. Here we use random numbers, that is as long as in addition key is to be used to be encrypted and decrypted single message, then it is discarded. Yes, and each new message requires new key. Such scheme is known as one-time pad. So it produces a random output that bears no statistical relationship to the plain text. So we have covered all these points, right? So here each message needs a unique key. So both sender and receiver must securely obtain and store this unique key. So here managing and distributing these exclusive keys without compromising is logistically complex and very risky. Okay, that's why we have told it as a theoretical approach. Okay, so let us look at this example. We have plain text, that is Apple, and random key generated XMPSB. This is very random, and from the sender and the receiver end, both should have the same key acquired and stored safely. Okay, let me write down plain text APPLE I have written, and the number equivalent also I have written. For A it is 0, for P it is 15, for L it is 11, for E it is 4. Next, I have key value XMPSB, its numeric equivalent I have written. Done. Now first thing I have to do is consider this A, that is the first alphabet, and then add it with the first alphabet of X. So 23 plus 0 is equal to 23. I got 23. Next, 15 plus 12. 15 plus 12 is 27. Next, I have 15 plus 15. 15 plus 15 is 30. 11 plus 18. 11 plus 18 is 29. Next, I have 4 plus 1. 4 plus 1 is 5. Now that I have obtained these, I have to write the numeric alphabetic equivalents. For 23, it is W. Sorry, for 23, it is X. For 27, 27 is not there here, right? So till 25 is there, 26, 27. So I can take B here. Next, 30. 27 is this, 28, 29, 30. This is E. Next I have 29. 29 is 25 was here, 26, 27, 28, 29. So it is D. Next 5. 5 is F. So this is how we get the cipher text. But there are two problems. That the first one is we have to generate large keys. So large keys need to be generated, which makes the encryption or the decryption very difficult for the attacker. But then speaking about the resources, memory is wasted here. And then when we are dealing with resource intensive tasks, this becomes a very big drawback. Then we have key distribution and management. That is, this secret key should be sent in such a way that it is very secure and the attacker does not get to know about it. So it is logistically complex and risky. So this was about one-time pad. I hope you have understood the concepts of monoalphabetic ciphers. If you have any doubts, do let me know in the comments. In the next video, we'll be discussing about the stream ciphers, block ciphers. We'll also speak about how the feastal structure works and how does the DS algorithm work. If you have any doubts, do let me know in the comments. And thank you.